Hello, I'm Kelly Davis. I work at Mozilla. I'm manager of the machine learning team there. First, I want to start my talk with a brief outline, sort of giving an overview of what it's going to be about. First, I'll start with the introduction, basically giving a framework for where the talk's going to go. Then I'll talk a little bit about why Mozilla is working on speech and why Mozilla is working on speech at this particular moment in time. Then I'll go into a little bit more detail on deep speech, our speech recognition algorithm and speech recognition models, and talk a bit about Common Voice, it's a project where we're open sourcing speech corpora. And then I'll go into a little bit more detail on future plans on both of these projects. So first, start with the introduction at the beginning. Generically, speech recognition really is, at a bird's eye view, relatively simple. You talk to a microphone, this audio gets digitized in a sequence of ones and zeros, and this sequence of ones and zeros is computed upon, resulting in text. This text transcript of the actual audio is an output from the process and interpreted as a particular result. As you all really know, sort of deep learning is a branch of machine learning concerned where the computational units, the fundamental computational units used are so-called artificial neurons, whose structure is motivated by, but not really slavishly following, the neurons in the brain. So my talk's going to really focus on the intersection of these two different topics of speech recognition and deep learning. So now I want to first talk a little bit about why Mozilla is interested in speech recognition. Mozilla is normally known as, let's say, a browser company. So why are we doing machine learning? Why are we doing speech recognition? Well, Mozilla generically is really guided by what's called a Mozilla manifesto. There's 10 different principles which relatively sort of guide Mozilla in sort of say uncharted waters. I won't bore you with all 10 of these principles. One thing I want to talk about is in particular one of these principles that states the internet is a global public resource that must remain open and accessible. Right now, speech recognition is becoming ever more prevalent as a user interface aspect and access of net-based information. However, speech really right now is siloed. There's a few companies that have production quality speech recognition engines and also the data to train them on. The open source world is really kind of left out in the cold. I mean, these other companies, sort of understandably so, keep their engines and also their data private. It's a competitive advantage. However, in the open source world, there's no really sort of alternative that's there. Part of the reason is that to create a speech recognition engine is relatively hard. Basically, you require a lot of data and you require a lot of compute. And to actually sort of have this in the open source world is a hard thing to do. So Mozilla's kind of taken speech recognition under its wing and is creating an open speech recognition engine, open speech recognition models, and also working on open speech data. So with that said, I'm going to move into a little bit more detail about Mozilla's speech recognition engine called Deep Speech. First, I'll start at a higher level and talk generically about what speech recognition engines require. Basically require 3 different ingredients. Require a speech algorithm, so algorithm plus code that is capable of turning speech into actual text. Or require compute, which is basically the computational resources to train this algorithm on. And also require speech data, so thousands and thousands of hours of speech of many people speaking along with the transcript of this audio. It's very much like a child learning how to speak, how to understand speech. It requires really a lot of data on the order of 10,000 hours of data, which is a little over a year of continuous audio, to train a speech recognition engine, to train a production quality speech recognition engine. So you can see why, at least in the open source world, it's hard to get this data and also associated with compute to compute on this 10,000 hours of data. So Mozilla has these 2 projects which we've initiated to actually try and solve this problem in the open source world. Deep Speech, which deals with the algorithmic problem and the compute problem, and also Common Voice, which deals with the speech data problem. I'll talk about Common Voice a little bit later, but first I'll go into a little bit more detail as to the architecture of the speech recognition algorithm used for deep speech. It's basically this. It's a simple, essentially, architecture. It's open, and also it's localizable. So those are sort of criteria we wanted to sort of have when we actually created this algorithm. It basically starts from the bottom up, being fed different speech features. These speech features are relatively simple. One has audio coming in and clips it into little audio windows. Each is about 32 milliseconds long. From each audio window, we extract a vector of features. The features we use are in particular MFCC features, which can be thought of as kind of glorified Fourier transforms in a way. A vector of these features have been fed to 3 different feed-forward layers, fully connected, and the width of these layers is about 2048. Well, actually is 2048. And then after that, we have a recurrent layer with LSTM cells in it. Finally, after that, we have another feed-forward layer, which is followed by a softmax layer. A softmax layer is kind of interesting. What it does, it outputs probabilities over characters. So for any particular window we're considering, it has a probabilities over the characters of the language you're dealing with. So it may say that A has probability 0.1, B has probability 0.2, or what have you, on and on. After the softmax layer, we have what's called the CTC algorithm. And the CTC algorithm solves what's called the alignment problem. So basically, I can say a particular word slowly, or I can say it slowly in a quicker way. Both of these have the same transcript. However, both of them, because the audio links differ, have different number of windows associated with them, and therefore a different number of characters coming out of the softmax layer. The CTC algorithm solves the problem of aligning these different widths, a different number of characters, with the actual transcript for both these utterances, which is the same, slowly. So that's basically the entire architecture, really, of the, at least of the acoustic model part of the speech recognition algorithm. Now I want to talk a little bit more about what we've done over the last year or so in sort of getting to this particular state of affairs. One of the things we tried to actually do over the last year is deal with small platform support. One of our goals really is not really to create state-of-the-art results. We're creating really good results, but also allowing these results to be deployed in many different locations. And as sort of part of that, we have tried to get as simple a model as possible. One of the things we did over the last year is just try and simplify things instead of complicate things. Initially, we had a bidirectional recurrent neural network layer in our model. We removed that and replaced it simply with a recurrent neural network layer. This almost half the size of our model, which is great as far as we're concerned. Another thing we also did, as a result of this bidirectional recurrent layer being removed, we can then add, with a few other changes to our model, TF Lite support. TensorFlow Lite basically usually doesn't handle bidirectional recurrent neural networks very well, but with the current neural networks and a few changes to our model, we can actually have TF Lite support there. And as a result of that, when we export our particular model, at least for the acoustic model itself, it's very small. It's 47 megabytes, which is really nothing in this sort of realm of things, compared to, say, multi-gigabyte models, which are really sort of hosted on servers. And with this sort of small model, we really had very little effect on word error rate. I mean, it basically stayed almost the same with all these model changes. And as a result of that, and the low computational overhead required for all this, we can actually run on smartphones. For example, we can do real-time decoding on something like a Snapdragon 835. By real-time here, I mean the time required to go from audio to text is less than the time of the audio itself. So basically, it's able to decode quicker than you can speak. Another thing which is a result of going from the thing we've done over the last year is in terms of going from bidirectional recurrent neural networks, we allowed actually now to stream information. So for a bidirectional recurrent neural network, I guess as you all know really right now, it consists really of 2 different recurrent neural networks. One going kind of forward in time, dealing with the first window, the second window, the third window of audio, and one going backwards in time, dealing with the last audio window, the penultimate audio window, and on and on and on. For a bidirectional recurrent neural network, it has to have the whole audio clip there before it can actually start decoding. This doesn't really lend itself to many use cases, for example, decoding phone calls while they're happening or live sporting events or what have you. So the switch to a recurrent neural network allows us to actually start streaming audio, actually decode the audio live as it comes in, sort of character by character. That's one sort of big plus of this. And as I mentioned also, it allows us to attack small platform devices much better and sort of deploy our speech recognition model on various different devices locally. Now I want to talk a little bit about some integrations we have of deep speech. These are either happened or about to happen. First, I'll talk about Firefox Reality. So Firefox Reality is a VR sort of mixed reality browser, let's say. It usually runs on a phone, and then you can maybe put it into Daydream sort of goggles and use it and sort of wear these goggles with the reality browser running in there. And also you can use it in terms of you can maybe have VR joysticks in your hand. So as you can see, when you're all sort of geared up like this, it really isn't useful to try and use a keyboard. I mean, your hands are full and you have goggles on. So voice is a really nice interface element that you can put in there. And so what we've done is integrated deep speech into Firefox Reality and allow you to control through voice various different aspects of the browser. Another thing we're doing, which is going to be released by the end of this year too, is that I guess Firefox really right now doesn't have an implementation of the web speech API. The web speech API itself is a JavaScript API that's used to do speech recognition and speech synthesis. So it's kind of falling behind in that regard, but what we're doing by the end of this year is releasing an implementation of the web speech API, and the speech recognition part of that is going to be backed by our speech recognition engine, Deep Speech. So it's going to be running in 2 modes, depending upon what device you're on. It'll either run on your device doing localized speech recognition, or if you have a lower power device, maybe it'll run sort of on a server somewhere. Those are internal to Mozilla. Externally, which is kind of interesting too, people have actually taken up deep speech. I'll just give 2 examples really right here. There's Ira Health, which is a Brazilian technology company that concentrates really on health-based technology. So what they've done is they've taken deep speech along with a corpus of Brazilian Portuguese and created a Brazilian Portuguese speech recognition model. Then what they've done is tune this to the healthcare sort of vocabulary and way of talking. And what they've done is deployed this to various different hospitals in Brazil to allow doctors and healthcare professionals to actually transcribe patient records easily and not having to write everything down. Another example of this is Te Haku Media, which is in New Zealand. They basically have various different media properties, and what they're doing now is they've taken deep speech along with a Maori speech corpus they have and created a Maori speech recognition engine. And they're using this to actually do transcription of their Maori radio show that they have. So that's it with deep speech. Now I'll talk a little bit more about Common Voice. As I mentioned before, Common Voice is really trying to solve the speech data problems, in particular the open speech data problem. It does this by crowdsourcing speech collection. More specifically, Common Voice is the web app that allows users to donate readings of various different sentences, of themselves reading various different sentences to a common speech corpora. Also what it allows people to do is donate validation. So you can hear another person reading a particular sentence, and you see the sentence, and you vote up or down if they read the sentence correctly, just to make sure that the data set is really sort of validated. So Common Voice over the last year has actually done several things, several interesting things. One of the things we've done over the last year is going from just English, which we started with because it was essentially the easiest thing to do. Now we're in, I think, 28 different languages we're collecting data in, and in the process of localizing our site and localizing Common Voice to 76 other languages. So we have essentially over 100 languages which are in flight. Another thing which we've done over the last year or so is we've released corpus of data from these various different languages. So our last release contained 18 different languages, and as far as I know, it's the largest multilingual open speech corpus that exists in the world, which is kind of nice. Another thing we've done over the last year too is introduce user profiles. So users can optionally sort of join the profile. Basically, with a profile, they can track their statistics. So for example, they can see how many clips they've recorded over a particular period of time. They can obtain awards for these clips, or they can have particular goals that can say, oh, I want to record an hour a week for Common Voice. In addition, if the user sort of consents to this, they can be a sort of member of this leaderboard. So you can see, like, for a particular language, who actually recorded the most or who had the most validations. So now I really want to conclude with some information about future plans for Common Voice and for deep speech. So first, talk a little bit about deep speech. I'll talk about deep speech first. So one of the things I mentioned earlier is that deep speech, the softmax layer of deep speech, really outputs to a particular alphabet what one is dealing with. As various different languages have various different alphabets, this particular part of the model is actually language dependent. What we want to do is make this language independent. And the way we're planning on doing this is basically as follows. You can think of, instead of having the softmax layer as it is now, one can have the softmax layer that outputs say, one of 256 different values. And then you can look at these 256 different values and interpret that as a byte, basically. And then what you can do further is you can look at sequences of these bytes and interpret these as UTF-8 characters. So this allows you to essentially have the model be the same for all different languages in the world, because Unicode more or less covers all the different written languages of the world. So you have a single model which can actually express anything in any different language. One of the reasons we're going to do this is very different advantages for doing this. So a few of them I can think of really right now. One, it actually has to do with languages that have very large character sets. So for example, simplified Chinese has in daily use maybe like 8,000 characters or something like this. And if you have a softmax layer in there with 8,000 different values, the model will become much, much bigger. And then deploying the model on, say, a smartphone would become almost impossible in a way. Another thing that's interesting about this model change is that it allows for transfer learning to be done really relatively easily. So I may train a model in English, and then I can use the same model because the architecture really stays the same. I can take that model and use some of the knowledge gained, say, in English and use it in another language where we have fewer resources, for example, Hakachin. Another advantage of actually this change in the model is that it allows you to do things like MAML, so whatever, model-independent meta-learning, where you can train on various different tasks, i.e. train on various different languages, and get a model initialization that's really good at learning a new language, say, for example, where you have fewer resources like Welsh or Hakachin or what have you. So that's one of the things we're planning on doing later this year. For Common Voice, one of the things we found out for Common Voice is that a lot of companies are really doing the similar thing to Common Voice. Basically, they're collecting speech corpora, but they're doing it kind of all in-house. And in talking to these other companies, we've really found it makes little sense for everyone to be doing more or less the same thing in times. And we want to create essentially partnerships or correlations between various different companies who are actually chipping in to actually collect this data. So then the cost of actually collecting data will go by, say, down by a factor of n. So that's two of the things we're really planning on doing sort of later this year and early next year. And if you want more information about deep speech and or Common Voice, you can follow links here, or you can just contact me too. Thanks, that's all I really wanted to say.